So, hi, thanks for coming. My name is Kristo. I work for a company called PlanetOS, which is a startup in Estonia. I work as a platform developer, doing mostly backend things with database, but also sometimes things on the front end. We'll get to those later. But yeah, we are a fairly young company. We started about 2 years ago, and basically what we do is so what we do is we provide sensor data search and visualization product. So here is basically a small overview of what our platform can do. What we can do is we can handle data from various instruments that are out in the real world, measuring things about the real world. These instruments produce various types of data, raster, time series, video, all kinds of different things. What we can then do is we can both spatially and temporarily index this data. And so this brings the question of who actually needs this kind of things. And the thing is that there is a lot of sensors in the world, and the number of sensors that are measuring things is growing really, really fast. And central sentence here is that it will outgrow social data volumes in a couple of years, because currently all the sort of big technologies are focused on data generated by humans, but the data generated by machines is pretty soon going to be faster. So now just to give a quick overview of how we actually do this, because the amount of data that needs to be processed is quite large. So on the technology side, what we use is columnar databases for data storage. Obviously, we work in the cloud using clusters to do the actual computing, and, MapReduce and Spark and all these interesting things. And so what the end result of this is basically is the ability to extract data from our index, both spatially and temporally. So basically what we have is at least 4-dimensional data sets, where the fourth dimension is time. And what we can do is we can extract slices or cubes from this data using our system. So for example, let's say you wanted to know what is the average temperature in the Indian Ocean in the year 2011. So we can answer a query like that pretty fast. And of course, you can search based on the devices that are generating it, or the time range, or the area, various properties actually. So the actual technologies that we use to accomplish this are well, mostly open source technologies actually, like RabbitMQ and Python and PostgreSQL. But to get best speed, for example, for columnar databases, we use Vertica, which is quite nice. Yeah, and various other things. But what we also do is we do the front end. We try to do nice visualizations with the data. This in the center here is our data studio, where you can actually explore the data. And the technologies behind this are, of course, front-end stuff. We use 3JS. It's a JavaScript application, HTML5 leaflet for maps. And as you saw in the previous slide, one of the central things of what we do is actually we show this data on the map. So one of the really important parts of this is that the sensors are actually out there, but the computer is right on your desk, and what we try to do is we try to connect back so you can get a very good overview of where the sensors actually are, what is the thing that they're measuring, and how the conditions are actually out there. And so for this, actually mapping is very important. And so that's why this talk is a lot about mapping. Let's talk about how maps actually are made. This picture here of a map, it has lots of different types of data on it. And it's actually, a lot of this data is sort of hand generated on this particular map, but what we try to do is we try to make most of these things happen automatically. And so just to get a very basic map, just to show things on the sensors, you can start with the elevation data. It's just the data about the height of the land surface at a particular point. Now, this doesn't actually give you that much in the sense that you can't actually even figure out if this particular area is covered by water or not based on the height, because in the center of the ocean, it's quite clear. If it's underwater, then, well, it's underwater. But on land, of course, there are many places that are below the surface level of the sea, but actually not covered by water. And but there's actually even a deeper problem here. What I talked about elevation. Well, what is elevation measured against? Right. So it's actually the main measurement is against the sea level. Right. But what is the sea level? So this picture here, for example, is taken in Israel, and this sign here shows the sea level, which quite clearly is not there. What this started with was that already quite some time ago, people decided that if we measure the average sea level, then this should give us a pretty good idea of where the sea level is. But of course, still, if you think about the sea at a particular point, how do you measure the average level? So it was accepted that the standard measurement to figure out what the sea level is, you take a measurement every hour for 19 years at the same spot, and then average all of these. And then you figure out the mean sea level at this particular spot. And of course, then they figured this seems pretty thorough. So if we do it at one point, then we can extend it to the whole country. Let's say in England, they did it in Cornwall, for example, in the beginning of the 19th century, figured out the mean sea level, and then said, well, this is the same around England. But of course, at the same time in France, they weren't sharing these things. They were doing the same thing, and also did it at a particular point, and then extended it to all of France. And then they also extended it here and figured out that it actually doesn't work that way. Because unfortunately, the actual world is a little bit more complicated than that. So what is the actual shape of the Earth? So it's definitely not a sphere. It's not actually even an ellipsoid, but it's called the geoid, is what the actual surface of the Earth is. And on the right side hand here, you can actually see a rendering of the geoid. But what is the geoid? So the geoid is the shape that the actual sea level has. Because the problem is that if you remove all the tides, all the currents, all the waves and wind effects, then this is actually the level of the sea that would be everywhere. But as you can see, it's different. It's not smooth. It differs everywhere. So this is actually what the problem is. Due to different gravity effects, it's actually the mean sea level varies globally. So it's not smooth. It's a rather complicated shape. But of course, this makes things rather complicated to deal with. And luckily, in most calculations, actually what people use is the reference ellipsoid, which sounds like it makes things easier, but unfortunately there are people around the world that have decided that the reference ellipsoid is different in different parts. So of course you have many standards to choose from as usual. Mostly the WGS84 standard is used, which was invented in Europe. But of course the Americans have their own, which is also interesting because the way they sort of decided is what the reference system, what it basically defines is a starting point and then how the coordinates go from there. And in the US, the guy that was assigned the task of figuring out the coordinate system, he had his farm, and he basically stuck a pole in the middle of his farm and said, well, this is the center, and we go from here. And there is actually still this plaque there saying that this is the center of the official North American coordinate system. And yeah, the end result is that actually if you take coordinates in the European system and then go to, let's say, Australia, and then to take the coordinates of the same place in the Australian system, then the difference is up to 200 meters. So, and this is mainly due to the fact that the actual shape of the Earth is this complicated, weird thing. And for example, the difference at the place where the Mount Everest is, the difference is actually, the height difference is more than 20 meters, depending on what you actually measure it against. So if you measure it against the mean sea level, which is the geoid, then it's higher than if you measure it against the ellipsoid that is used in most modeling calculations. And what the interesting thing here is actually also is the GPS GPS system uses also the ellipse for the coordinate calculation. But of course, when you're in the real world, you have to take into account the geoid. And so what basically each GPS device has inside is a map of the world, which says what is the difference in this particular point between the geoid and the ellipse. So they do the calculations on the ellipse, and then they add this magic number that fixes the coordinate at a particular location. You know, there's a joke in science that we assume a frictionless spherical cow in a vacuum. Anybody know this joke? No? Okay, so the joke is that there is this farm somewhere. It's having problems with its cows, and they're not producing enough milk. And so there's a university nearby, and then they go to this university and ask the scientist that we have this problem, the cows are not producing milk, can you help us maybe? And then the scientists, they say, yes, of course. And then they deliberate for a couple of weeks, and they come back and say, we have found the solution, we know what the problem is. There is a slight thing that we have to tell you. We had to assume that the cows are frictionless and spherical. That's what we're doing in regards to coordinate calculations on the Earth. But this was all very complicated stuff, so there's actually a small quiz. This is a fairly zoomed in map of a particular place. And the question is, what is special about this place? Can anybody actually tell me straight away? Sorry? It's not on top of a mountain, but you're sort of getting a little bit closer, I have to say. The name of the place is Tall Lake, if that helps anybody. No? Okay. Let's say it's sometimes nature has this interesting property that it likes recursive structures. For instance, like cauliflower, it's basically a recursive structure. It has the stem goes into smaller stems that look exactly like the bigger stem. So this is actually a geographical example of this. And so anybody want to guess?
It's a lake inside, on an island inside the lake.
That's almost there, but the real answer is that, of course, it's an island on a lake, in an island, on a lake, in an island. And this is actually, it's in India, but there are a couple of more of those in Canada, in the northern parts. So yeah, nature is somewhat strange. There are interesting features, like there used to be a natural nuclear reactor inside in the Africa, in the center of Africa. This Okla is the place is called, where actually what it happened inside the ground, that there was a very strong concentration of uranium deposits, and then was a stream of water flowing by, and it moderated exactly so that there was a naturally occurring nuclear reaction which was moderated by the water, and so it was producing heat for probably a couple of 100,000 years. But it's stopped now. But yeah, so let's get back to actually mapping. So we talked about how the world actually looks like. But now the next problem with mapping is that, okay, we know that the way the world is, but a map is a two-dimensional thing and the Earth is a three-dimensional thing, right? So what we need to do is we need to take the three-dimensional object, which is somewhat spherical, and extend it onto a plane. Now, this requires that you have to distort or cut the surface in order to be able to extend it onto a plane. So this is what map projections basically are. Here are a couple of more strange examples. There are different properties to different projections. Some of them preserve area, some of them preserve angles, and various other types. There's a gnomonic projection that actually preserves the minimum distance between points. We won't get into those. Instead, I'll just show you a couple of the more commonly used ones. So the first one is Mercator. If you use Google Maps, then, well, you use this one. The way this projection is done is, as you see on the left side there, you take a plane, you wrap it around the equator of the Earth, and then from the center of the Earth, you start drawing lines. And for each point on the plane, you draw a line to the center of the Earth, and then you take the point where it intersects with the surface, and then you draw this point on the plane. So the end result of this is that you get a complete projection, but unfortunately the plane has to be infinite, but we'll get to that in a moment. So this was invented by Gerardus Mercator, who was an avid sailor, and this is used quite a bit in navigation. And the good thing about this is that it has straight rhumb lines. Well, this probably doesn't mean anything to anybody here, but the idea is that if you set a course on a ship, and then it looks like you're going straight, right? What actually happens is if you set a course on a ship and then would drive along the same course, the same heading, then you actually start to make a sort of, not a circle, but this type of line around the Earth. But the good thing about this is that you can draw this on a Mercator map as a straight line. So in different projections, it's actually not a straight line. And it's also not the shortest distance, but what mostly is done in navigation is you say that today we're going to sail this much, and then you draw a straight line on the map, take the heading of the line, and then keep the heading, and then you pretty much end up in the same place if you account for wind and other effects. So this was very useful in that area. But there are also problems. So of course the main problem with it is that it heavily distorts the polar areas, which is of course also the reason why it was used so much in the previous centuries, because mostly shipping was done near the equator, and near the equator it's a pretty precise thing. So here what you see is actually screenshots of a Mercator projected map from Greenland and Africa, and they are pretty much exactly the same size if you take the screenshots. But of course in reality Africa is about 15 times larger than Greenland. So you can get the wrong impression just looking at that. And so basically what really happens is above or below 70 degrees latitude, the Mercator projection is pretty much useless and not really used. So let's take an example of a projection that is used in Arctic areas, which is the Arctic Stereographic, or polar stereographic to be precise. And so a stereographic projection is so that you take a surface where one point of the surface is actually touching the sphere. And so you take the farthest point on the sphere, which is probably across exactly, and from this point you again start drawing lines onto each point of the surface that you're projecting to. And then again you take the point where the line intersects the globe, and you color the surface using the data about that point. So the nice thing about this is that, which is perhaps not immediately intuitive, is that using this you can actually look at the Earth from a polar standpoint, from the pole, but you can actually see on the other side as well. So you can map the points on the other side of the equator also on using this stereographic projection. So if you just look at the sphere, right, you can't see the other side, but using this you can, which is a little bit useful. But of course, the problem here also is that it heavily distorts the areas as you get closer to the other side of the globe. So usually what is done is you have one projection from the Arctic side and one from the Antarctic side. And so as you cross the globe, you switch between those. And of course, this is more and more used in recent times because more and more activity is actually moving towards the poles. There's, oil and gas things are more and more drilling is done near the polar areas. There is more research in extreme environments. Now that in the northern side there is less ice due to, I won't say global warming, I'll say climate effects. Then there are new shipping routes that can actually go faster because they can go through the North Passage now. And so yeah, this is actually becoming more and more important. And there, of course, in addition to this, there are many other types of projections that look weird and are not used that much, but some of them are useful in terms, because for different applications it's important to preserve different properties of a map. For example, the reason why Mercator projection is used by Google Maps is that it preserves angles. Right? So this means that if you look at the intersection of roads on a map, then the intersection, is an actual intersection where the roads cross at 90-degree angles. But of course, the length of the roads doesn't actually correspond to the real world. But there is other types of projections that preserve areas where each area is the same size as it is actually on the globe. But then the angles sadly get distorted. So as I said previously, there is no sort of best solution. You have to have a trade-off at some point. Okay, so that was maps. So now you know how to do them. But the next question is, of course, what to show on these maps. So let's talk more about what kind of things are actually out there measuring various properties. So in our system, we have this website called marineexplore.org, which is our public data community site where we collect publicly available data. This is data made available by various research institutions and universities. What we do is we collect them from various sources. And most of these sources are in different formats, and you have to access them in different ways. And what we do is we make them easily searchable and easily accessible. So you can just use one protocol to access all of this data. And we're working with more than 33 organizations and there are actually more than 40,000 devices that are in the system. These devices range from tags attached to seals, to unmanned vehicles or submarines, and of course there are many, many things in between. For example, it's an interesting project is Argo. These are floats. These are sort of buoys that freely float around the ocean, and every now and then they decide that they will go down. Okay, and then they lose all the oxygen inside them, and they drop down to whatever depth the ocean happens to be there. And then they, as they come back up, pumping the water out, then they take measurements of the properties of the water. And there are various types, like pressure, salinity, chlorophyll, all kinds of the number of different measurement types is in the hundreds. And then they come back up to the surface, and then use satellites to transmit this data to the university, and then the university transmits this data to us. And we make this available. Anybody can go and download. And the oldest data set is more than 100 years old and continuously updated. It's about river water flows, so which measures how much water is actually flowing through rivers around the globe. But there is also data from radars and satellites, which are sort of remote measuring devices instead of in situ device which measures the properties around it. So there are actually various satellite products, some of which are post-processed and actually modeled using different properties. And this is actually a really for me, it's a very interesting thing, because, for instance, there is a measurement of wind speed from satellites, global wind speed. So this sort of begs the question of, how do you measure wind speed from a satellite 300 kilometers away? So, and what actually is done is they use radar to measure the surface of the water. And so what wind does, it sort of disturbs the water surface a little bit, so it starts to ripple. So, but the ripples are extremely tiny, I mean, on the order of millimeters, right? And so what they do is they measure these ripples from a satellite orbiting God knows how far away, and then from these ripples, they extract enough information to determine the wind speed on the ocean surface, which sounds pretty amazing, actually, for me at least. And there are many satellite data products. There's Landsat, for example, which takes images at very high resolution. So once every 16 days, it generates 10 terabytes of data from 12 different layers using different wavelengths. And you get to find out these sort of interesting projects. There's, in the US, there is this agency called NRO, the National Reconnaissance Office, which is sort of the secret arm of the NSA. And what they do is they manage spy satellites. And from time to time, when they sort of figure that this satellite is too old for us to use, they give access to it to scientists. So from time to time, you get this this proposal calls for proposals where you can propose that if we had a satellite that did this, then we would use it to do this kind of science, right? And actually, the latest call for proposals included a month of time on a satellite that had cameras and several wavelengths with a resolution of 1 centimeter per pixel, right? So if you look at Google Maps, for example, they use this keyhole satellite data, for example, and the commercially available satellites that anybody can buy data from, they are the highest resolution that you can buy is 1 meter per pixel. But of course, if you are a scientist and can get the NRO grant, then you get access to an old satellite that they don't want to use anymore, which has a resolution of 1 centimeter per pixel, which is an interesting data point. But I also to show you a little bit about what we can do with this data. In addition to searching it, we can visualize it. So here you see actually various types of visualizations that we can do. So starting from the top left, you can have just devices where their locations are and what trajectories they have taken. Then these are in situ devices. That some of these are powered and go where the owner wants them to go. Some of these are stational, like anchored buoys, and some of these are just drifting around the ocean randomly. Then you have radar data, which is gridded data, which is in 2 dimensions. And it's actually, the image here is about wind speed, I believe. And this is fairly high resolution data, and well, actually in this sort of data sets, the couple of 100 meters square resolution is per pixel is actually quite high resolution data already. And then here is the GHRST. This is a model run by NASA that actually incorporates various satellite data products to produce high resolution global temperature data on the sea surface. Yeah, what we can also do is we can do quiver plots, which show the basically vectors where for example, for the wind speed, you can see the direction where the wind is, and below it, the blue on the bottom left is the speed of the wind blowing at that particular point. And of course, you can just look at graphs from measurements from these in situ devices. And another, on the bottom right here, there's this interesting thing called ADCP, which is a measuring device that you drop down into the ocean, and then it actually takes sort of 2-dimensional slice as it goes down and comes back up of this particular location. And so you drop it at various places, and then you get the continuous 2-dimensional slice of the ocean that you can actually look at. So these are our 2D visualizations, but we also do 3D things. So here is actually data about noise. So what you see here is actually it's a 3D grid of noise data. Let's say it's a ship that generates this noise, and you can actually model and measure how this noise goes around in the ocean. And this is used mostly for environmental purposes. For example, if a company wants to do something in the ocean, like an oil company wants to drill a well, then what they have to do is they have to do sound simulations and studies where they see how much the sound affects the local wildlife, sound of the drilling, sound of the ships, things like that. And you might think, well, okay, how much can one local thing really affect the ocean? But of course, we have also for us Chris Clark, who works for us, who is a scientist in Cornell University, used to be. He's an expert in whales. He can tell a lot of interesting stories. So the thing about sound and the water is that sound travels extremely well in water. So, for example, whales, what was found out fairly lately actually, is that they communicate, they talk a lot to each other. But the reason why we didn't know this is that wavelength they use for communication is extremely low. It's very low frequency waves. But the decibel levels that they can output are pretty good. I mean, I'm guessing most of those can do better than your car stereo, unless you're one of those guys who do the dB drag racing thing. So a wave can output actually 120 decibels of noise, or not noise, but actually communication. So the interesting thing is that this noise can travel all around the Earth. So actually whales, what they can do is they can talk to each other even the other whale is on the other side of the Earth, which is pretty cool. Of course, we don't know what they're saying yet, sadly. But this sort of gives you an idea of when you think about like drilling. Oh, yeah, you have a question. Okay. So this gives you an idea about how this, and the noise made by ships and drilling, for example, is also very low frequency noise, and this gives you an idea how much it can actually affect. And there is a lot of studies being done on how this affects the wildlife and marine life. And also, of course, there is this other use case where you have this sort of image depicts various sensors installed a particular plant. Well, this is Alaska, and the scale is, of course, ridiculous, but it's just an illustration. And so what we can do is we can take the data from these sensors and show it interactively on a 3D map. So you can see what's actually going on and where the temperature, for example, it is too high or something like that. So, anybody have any questions? Yes.
How much real-time data do you handle?
For the public data side, I think the lowest update time is 15 minutes. So the reason for that is that actually the measurements aren't usually done that often in these public devices, and what they do is we don't directly connect to them, but there is a university or organization that manages these. They get the data from them and then from the actual device, and then we get the data from the organization. So there is a delay. But for the commercial side, where we offer this service to actual private companies, the update times can be a lot less than that. We don't do sort of this like real-time video or stuff like this. We don't do that. But we can do, let's say, near real-time. Any other questions? No? Okay. Well, thank you for coming.